In this lecture, we will derive the standard form of Maxwell's equations from the relativistic covariant form. To begin with, we will reiterate that we define this symbol, partial with a lower mu, to be, by definition, the partial with respect to x upper mu. Specifically, this vector, this is a linear vector operator, differential operator, that has four components: partial with respect to ct, partial with respect to x, partial with respect to y, partial with respect to z, which we're very familiar with. Remember, it is the upper or contravariant components that are exactly the same as x, y, z, and t. Therefore, when I take the derivative with respect to these components, that is what I am doing. We notice here also that although this is a contravariant component, when I take the derivative with respect to it, that object is actually something that transforms as though it has a covariant component. Therefore, the derivatives with respect to a contravariant vector is itself a covariant vector. Maxwell's equations in the relativistic form look like this. Partial mu of f mu nu is equal to mu naught constant times j nu. Well, we have to take these for a whole set of different nu's. We will take nu is equal to 0 first and look at what this equation is. Now actually, what we're doing here is not just doing the derivation. The main part that we're trying to accomplish is for everyone to be very comfortable with both the summation convention and the covariant relativistic notation. So in fact, we're going to start out here and say let nu equal to 0, and then we must automatically perform the sum over mu over all values. Mu is equal to 0, to 1, to 2, and to 3. All the while keeping nu is equal to 0, and on the right hand side we will have mu naught J0. Now J0, you will recall, is c times rho, which is the charge density as a function of x, y, z, and t. Well, f mu nu is an antisymmetric tensor, and its diagonal components vanish. Therefore, f00 vanishes. We're then left with three other components: partial 1 of f10, partial 2 of f20, and so forth. f10, you will recall, is ex over c, f20 ey over c, and f30 ez over c. Now that is, partial with respect to a lower 1 is a partial with respect to an upper 1, which is partial with respect to x itself. So therefore we end up with the equation 1 over c, because we factor to c outside. These are the partials with respect to x, y, and z of ex, ey, and ez. So that is our familiar expression of the divergence of the electric field. Del dot E is going to be equal to mu naught c times rho, taking c and multiplying it by the other side, and recalling that c is equal to 1 over the square root of mu naught epsilon naught. We then are able to cancel the mu naught and are left with a 1 over epsilon naught right here. Consequently, we get the first of Maxwell's equations, del dot E is equal to rho over epsilon naught. And that comes exactly from this first equation where the nu is equal to 0. Next, we're going to take nu is equal to 1, and when we do that, we get partial FOO with respect of F1. F1 here, 1, 1. This is the partial 1 of F11, partial 2 of F21, partial 3 of F31. And in this case, we get mu naught J1 because we're taking the first component of this entire vector equation. F01 is minus ex over c. F21 is bz, and F31 is minus by. Now, this term, of course, vanishes because F11 is antisymmetric and the diagonal terms vanish. We're therefore left with, in this first term, we have a 1 over c squared, partial of e. I brought it now to the right-hand side. It was negative here, So I've got a 1 over c squared from these two factors of c, partial of e with respect to t. And it's positive because I've taken it to the right-hand side. I also have the term mu naught j, but j upper 1, you recall, is j in the x direction, the standard component of the current density in the x direction. I'm then left with two other components of the equation, partial with respect to y of bz and partial with respect to z of by with a minus sign. Well, this is exactly the x component of the cross product, del cross b. Remember, the x component is partial with respect of y of the zth component minus partial with respect to z of the yth component. So this is del cross b for the x component, mu naught times jx component, times 1 over c squared is mu naught epsilon naught partial of e with respect to t for the x component. Obviously, if this is true for the x component, if this is true for the x component, then this will be true for the y component and the z component also. This then gives us the other three of these Maxwell's equations. Del cross b is mu naught j plus mu naught epsilon naught partial of e with respect to t, and that e is a vector. And one notices that both of those two equations we just derived were, quote, the inhomogeneous Maxwell's equations. That is, the right-hand side had the current density or the charge density. There are two other equations called the homogeneous Maxwell's equations, and they actually come from the dual tensor. And one can write them. There are two ways to approach this. We'll first approach it from the point of view of using the dual tensor equation. Partial of mu of g mu nu is equal to 0, where we define this dual tensor to f as g mu nu is equal to 1/2 epsilon mu nu lower rho sigma f rho sigma. The 1/2 actually comes from the fact that this epsilon symbol is going to pick up these different f terms twice, and the 1/2 will cancel that. It should be left as an exercise to the reader to see if you can derive this exact expression for g mu nu. They're just simple terms. For example, if you're looking at the 0th row and first column, 0, 1, then you'd put a 0, 1 here, sum this over all two 3's, and you will find that with those two 3's you get exactly 1 bx. Likewise, we get a by of bz minus bx, by, and bz, and the electric field are in these positions. This also is a totally antisymmetric tensor, and we have used here the expression where epsilon 0, 1, 2, 3 with all lower letters is equal to plus 1. Now there are two equations that are homogeneous that can follow from this equation right here. And you'll notice that in the dual tensor, the electric and the magnetic fields have exactly changed roles, where the magnetic field is now in the time column and the time row, whereas the electric field is in the spatial part. Proceeding with this equation, we now start out with G01. G01 we can actually show is, now I'm going to do this derivation right here, 1/2 of epsilon 0, 1, 2, 3 F23 plus epsilon 0, 1, 3, 2 F32. There are no other possibilities that are non-vanishing, because recall that epsilon must have all four components as transpositions of 0, 1, 2, and 3, and no two can be the same. In this first one, F23 is minus Bx, and the F01, 2, 3 is minus 1. We can see that because if we drop a 0, and then we do not change the sign, but if we drop a spatial index 1, we do change the sign. Therefore, we have changed the sign once away from a positive sign, which means that this would be equal to a minus, in lowering this index, minus a minus Bx. The other term, we do that again, and we get a cancellation for the F23. we get 3, 2. We get a minus sign here, but when we interchange 3 and 2, we get another minus sign, which gives us overall a plus sign for this object right here, the totally antisymmetric tensor. Then F32 is a positive bx. So now we have 1/2 of bx plus bx, which is bx itself, and we've proved this term here. Likewise, G12 we can see is 1/2 of epsilon 1, 2, 3, 0. The 1, 2 comes from here. 3, 0 has to match the F30. And likewise, we have a 2, 1, epsilon 0, 3. To begin with, the F30 is a minus EZ over C. I'm sorry, it's a plus EZ over C. And this term right here, when we drop this index, we get a minus sign. Here we get another minus sign, so we get 2 minus signs, so it's positive. So we have now an epsilon 1, 2, 3, 0. To bring the 0 back into the normal position, it has to transpose with 1, 2, 3 elements to get to the far left side. Therefore, this whole term is a minus 1. Likewise, this term here, there's an error right here. This should have been epsilon 1, 2, 0, 3. Please change that. Times F03. The F03 is a minus EZ over C. But this term, which contains, since it's a 1, 2, 0, 3, is one transposition away from this one, so it is positive rather than negative. So we therefore get two terms that are both minus EZ over C times a 1/2, which gives us minus EZ over C. So that proves to us that the 0, 1, 2 term is a minus EZ over C. And so we have just derived this term right here, and just a moment ago we derived this term right here. Consequently, one can proceed in that way to rederive all of the terms in this antisymmetric tensor. One of the key things to remember is that in the temporal part, when all of these are positive, all of these are negative, or vice versa, because it's antisymmetric. But in these, the negative sign appears twice on two of the spatial ones, and a positive sign appears on the other spatial one. That has to do with the cyclic permutations of 1, 2, and 3 are different in those two cases. We now continue with the derivation of the two homogeneous Maxwell's equations. Recalling partial mu of G mu nu equal to 0, we take first the value nu is equal to 0, leaving us with partial 0 of G0, 0 plus partial 1 of G1, 0, partial 2 of G2, 0, and so forth. Now as we write these out, we notice that G0, 0 vanishes, and we're left for these other three terms, G1, 0, 2, 0, and so forth, a minus bx, minus by, and minus bz. The derivative is respect to an x, a lower 1, which is a derivative with respect to the contravariant, or the regular x. So we have partial with respect to x of bx. All of these with minus signs, so we get minus del dot b is equal to 0. Thus, del dot b is equal to 0 because we can multiply both sides by a negative sign. That proves the third of Maxwell's equations, equivalent to the Gauss's law for magnetism. Next, we will take the first component, and when we do that, we get partial mu of G mu 1, and it looks like there's one term missing here. This should be a G 0, 1, G11, G21, and G31. There's a typo there, or misprint. Writing these out, this first term, G01, is the partial of Bx with respect to Ct. The G11 vanishes, so it's 0. The G21 is EZ over C with respect to Y, or x2. And finally, the G30 is minus EY over C with respect to Z. All of that will equal to 0. Writing that out slightly differently, we have 1 over C here, partial of Bx with respect to T, plus, and now we have two terms. We pull the 1 over C out to the front, and we have partial of EZ with respect to Y. Remember, the x upper 2 is equal to Y, minus, from this minus sign here, partial of EY with respect to Z. Obviously then, by taking this term to the other side, we realize that that becomes a minus sign, and we're left then with the x component of del cross E is equal to minus, and there's a 1 over C that cancels through the whole equation, so that disappears, partial of B with respect to T. This is the second of the homogeneous Maxwell's equations. And in conclusion, we can see that the partial of F mu nu is equal to mu naught J nu gives us two equations. Gauss's equations for electricity, these are the two inhomogeneous equations, and del cross B, which is mu naught J plus mu naught epsilon naught partial of E with respect to T. The other of those are the two homogeneous equations, which are done in terms of the dual tensor to F mu nu called G mu nu. It's equal to 0 here. Del dot B is equal to 0. Del cross E is equal to minus partial of B with respect to T. So we see that the inhomogeneity comes from the fact that this equation here is inhomogeneous and this is homogeneous. Therefore, these two terms that appear here in these homogeneous equations do not appear down here. Otherwise, the equations would be symmetric. A very important observation that one should make right here is, of course, the fact that these terms here arise because charge, electrical charge, is the source for the electric field, and these electrical currents are the source of the magnetic field. What if we had magnetic monopoles? If there were magnetic monopoles, as there are electric poles, then we would have another term here for this dual tensor, and it would take the form of a constant times a current for the magnetic monopoles. And then that would manifest itself exactly in symmetric equations right here, where we would end up right here instead of 0, we would have a monopole density divided by a constant, and over here an extra term, monopole current, multiplied by a constant. So if we were to find monopoles in the universe, that's the way we would modify the homogeneous equations to have two dual inhomogeneous equations. These for the electrical currents in the electrical monopole and its currents, and here for the magnetic monopole and its currents. However, in the next derivation, we'll see something very interesting. I want to assume now that we have a 4-vector potential. If we have a 4-vector potential, then we find that F mu nu is by definition partial mu of A nu minus partial nu of A mu. If that's true, then we can find out what the derivative partial mu of G mu nu is. And we can write it immediately in this form, because G mu nu can be written as the totally antisymmetric tensor times F mu nu, which we write here. So you'll notice we've got the partial mu, and then we replace G mu nu with the dual tensor expression of F mu nu, which is derived from this expression right here. So we plug that in here. Now what is that going to be? Well, we end up with something very, very interesting. We have the 1/2 here. We pull the epsilon symbol out front, and we are left then with a partial mu partial rho of A sigma minus partial mu partial rho A sigma. Now, it is important to realize, and that's part of the problem, part of the task that we have before us here, is to practice with tensor and vector indices and the mathematics before we get to the Lie group expressions. We notice that anytime we have a summation over an index, then we have a lower and an upper index, we can make one upper and one lower. So if we wish, we can change, as we have done right here, we can take this mu index here and raise it and lower the mu index right here. We also can interchange the order of the mu and nu, which we have done here, and make the mu over here. Then we lowered the mu and raised that mu, which meant no change. The first interchange gave us a minus sign, because anytime we change epsilon, if we transpose two of the indices, we get a minus sign. So you can see from right here at first, I take the nu, flip it over here, that gives us a minus sign. I'm left with the mu in the an uppercase mu, and an uppercase mu right here, and I'm sorry, yeah, that's right, uppercase mu with a lowercase partial mu. I can raise this partial mu so that it takes this form right here. Likewise, I can do the same thing with the second expression, taking this mu and raising it and doing the interchange. As a result, what we get is an expression that looks like this and then has partial mu partial rho of A sigma. Well, the incredible thing here is that this is the two partials multiplied together, or acting one after the other, is a symmetric form. And this, with mu and rho here, is a totally antisymmetric form. It is a very important result of tensor analysis that if we have an antisymmetric tensor index contracted with a symmetric tensor index, the term is automatically totally zero. That's because if we interchange for every one of the terms where we have a mu nu, there's another term equal to it with nu mu, which is identical here but has a minus sign with the epsilon. Consequently, we can make the following far-ranging statement. If the electromagnetic field tensor F mu nu is derivable from a 4-potential A mu, then it follows that the partial mu of G mu nu is equal to 0 automatically. And the other of two Maxwell's equations is satisfied. Therefore, if magnetic monopoles are found, it follows that K mu, which would be something like C sigma, that would be the monopole density for the dot component in K for the current density, would give us a new type of equation like this for a K mu density like the J mu density, where rho naught replaces mu naught. And another consequence is that F mu nu cannot be equal to the derivatives of a vector potential. That's a very far-ranging result.